So anyway, yes, so this is a discussion on challenges experienced with liquid cooling, and we've got a lineup that, a stellar lineup of people that have had experiences with liquid cooling over many years. This session is coming across 4 time zones, as I understand it, across the pond between Europe and the US. And I think it's fair to say that liquid is here. I didn't introduce myself, sorry, it's John Summers. I'm scientific lead at Research Institutes of Sweden, based in Sweden now. I'm a Brit originally, done my Brexit, got that done and dusted, and gone to Sweden. And over there, we're doing all things with regard to data centers. And I have sort of worked in thermal management as a researcher for over 12 years now. And the institute that I'm working with in the north of Sweden is focused on thermal management of data centers. In fact, it's all aspects of sustainability and energy. So what I thought we would do is we have 5 panelists here coming from with different backgrounds and different takes on liquid cooling. So what we have is we have a slide from each panelist to sort of describe their experiences with liquid cooling, and I've done it in alphabetical order, and each person will talk to their slide, each panelist will talk to their slide and introduce themselves at the same time. So if we go to the next slide, please. And then I'm going to hand over to Tim to speak for a couple of minutes about himself and his experiences with liquid cooling.
Hi, my name's Tim Chambers. I'm a director of Exuviate. We're very much into designing what we would call energy efficient data centers, and we see immersion and liquid as a major driver for that. What you've got on the screen here, I've been in data centers since 1986, so I've seen data centers change a lot. What's quite nice, and certainly from the panel we've heard before, is the fact that we're now entering a new sort of experience now where technology is starting to drive the data center designs forward again, which is quite exciting. As I say, I come from a background where we didn't have racks. We originally started on shelves, so liquid cooling is something which is really quite exciting. What we've got on the slide here is what we built in Lincoln, where we did a hybrid solution of different types of technologies and basically did a cascade solution with the heat. So as you go from left to right, the temperatures rise. We then proved heat recovery. So one of the things we, again, go back to previous panel, we proved was the fact that we could mix technology, but also the fact we could actually have a useful end product. As I say, I've been in data centers a long time where waste products from a data center is just pumped without any thought. What we're finding now is waste heat is something that's usable and is actually something which is actually a useful product for either reuse in buildings or even something you can actually sell.
Okay, so sorry, I lost sound for a moment there. So if we can move on to the next slide. Thanks, Tim. I think the next slide is Jessica's going to speak to from Intel.
Yep. Hi, everyone. Jessica Goldbrand. So the Intel liquid cooling, the way that we are working with liquid cooling, right? We have liquid cooled products. So showing a server, a Walker Pass system here to the right that is liquid cooled. We are also working on ecosystem enabling to make sure that the liquid cool solutions are available for, of course, our products as TDPs and powers and densities are going up. And I've been talking about the ecosystem enabling previously within OCP as well. So we got the liquid cooled IT equipment, if it's either hybrid solutions that are using air and liquid versus full liquid cooled solutions as well. Of course, there's many challenges with that. But depending upon really what the cooling capability is and the TCO, what are are the customer really willing to pay for it, right? Of how much that they potentially wants to divide up in how much to capture within liquid versus how much to capture of the heat in the air. Some design considerations for liquid cooling, right, is talked about this a lot today in regards to wetted materials compatibility with cooling fluids, to make sure that all the wetted materials are compatible with the cooling fluid used. And that's part of the ecosystem enabling that we're doing at Intel, and we share that information with the OCP. And we're also developed the Universal Quick Disconnect, the UQD, that was just presented to the incubation committee, and hopefully we can get that approved and officially submitted to OCP. But one of the things that I wanted to highlight as well, not only wetted materials, right? And I should say also that the UQD, the idea behind that is really of making sure that it doesn't matter who you're buying a quick disconnect from, who the manufacturer is, but you should be able to take a server, take it out, as long as it's a UQD of the same type of dimensions, you'll be able to plug in the other server system that you're potentially want to upgrade with. That's the idea of making it easy, right, for the customers to use liquid cooling. But one of the things that are essential here is really the integration, right? So yes, we can provide a part, right? If you're having the IT equipment, that's only part of the solution, only part of the cooling loop, right? We talked about the TCS cooling loop, the secondary loop, or the technology cooling system. You have the IT equipment, you need to make sure that that goes into the rack manifold and to the CDU, and then the CDU to the facility system. You need to look at it from a holistic point of view, and of buying components separately and not looking at it as a holistic implementation. That's when a lot of people can get into trouble with doing that. So that's my experience, and would like to hand it off to the next speaker.
Hey, John, it looks like you're on mute.
Yes, I'm on mute again. I apologize. Yes, it's over to Steve Hammond now from NREL. If they get to the next slide.
Thanks, John.
Thanks.
I apologize. I've got 2 dogs and they've been napping all afternoon, and within the last 5 minutes they decided they need attention. But so bear with me for a second. So I'm Steve Hammond. I'm a senior research advisor at the National Renewable Energy Laboratory. It's a DOE lab just outside of Denver, Colorado. Been at the lab for 19 years, and we started planning our new HPC data center. It was new at the time. We started planning in 2009. It was commissioned in 2012. It's a showcase research facility. The data center sort of sits in the middle between office space to the right and laboratory space to the left. Usable, raised, uninterrupted floor space, 10,000 square feet. It's capable of supporting 10 megawatts of IT load. It was a LEED Platinum facility overall, including the data center. We had a design target of a PUE of 1.06 or better. I think our trailing 12-month PUE is 1.03. I checked, it was like 1.026, but at some point you get to diminishing returns. There's no mechanical cooling, so it's all evaporative cooling, and some actually non-evaporative cooling we've done with the Johnson Controls. We focused on getting at least 90% of the IT heat load to liquid through direct component level liquid cooling. So it's warm water supply, 25 up to 25 C on the cooling supply. And one of our design constraints was we wanted at least 35 C return water back, because we've focused on waste heat capture and reuse as well. And designed that, we had a holistic sort of chips to bricks view, not just of the data center, but of the entire facility. So the heating and occupied spaces was paired with what we could get from the waste heat capture. One of the things was, for Denver, we had to consider what was the coolest we could get water using evaporative means only on the worst days of the summer. And for the building perspective, for building, creature comforts, what would be the coolest water that we could get from the data center and still keep the building warm in the coldest days of winter in Colorado? So those were sort of two design constraints that said, okay, as long as the waste heat that we capture off of our data center is at least 35 C, we can feed that into the heating system. So we use active chilled beam in the occupied spaces. So we've been operating the data center for 8 years. The worst water incident we had in the building was in one of the kitchenettes. We really didn't have any water issues in the data center. We had a commercial coffee pot that overflowed, that we never had any issues in the data center. So I think some of the topics will come up through the discussion, but happy to turn it over to Robert, and then we can discuss when it comes to question and answer.
Thanks, Steve. Yeah, so if we go to the next slide for Robert to speak to Robert from Microsoft.
Hi, everyone. I'm Robert Langston from Microsoft. I'm a senior hardware engineering manager in their cloud hardware development division. So the group I work with does thermal engineering for a large majority of the cloud servers that go into Microsoft data centers. As Microsoft, we may be a little newer to liquid cooling than some of the other folks on the line. So we've run several experimental systems looking at all forms of liquid cooling, from immersion to cold plate cooling. And we have a few POCs and small scale liquid cooled deployments that have hit our data centers. Some of the challenges that we faced is the readiness of our air-cooled facilities to accept liquid cooling. At least within Microsoft, a lot of the facilities aren't easily plumbed for liquid. There's not a lot of fluid lines running on the floor and things like that. So rolling a liquid cooled rack into the data centers is challenging and requires a lot of retrofit and shutting down of services. So looking at how to minimize that, particularly with the large number of air-cooled data centers we have, is priority going forward as we look at scaling up. More other challenges are a new service model and monitoring for the liquid systems in the data center. It's just something that data center technicians aren't used to seeing in most of our data centers. Getting everybody trained up and figuring out, what do we monitor in the systems? What kind of failure modes are there? How do we and what kind of event or service events do we trigger if we do see a failure, a leak, or anything like that? Other challenges we've seen are the cost and compatibility of liquid components. I think Jessica talked to this a bit, and as we scale up, we want to be able to have interchangeable fluids, interchangeable components, and be able to integrate systems from multiple vendors and put a lot of different things in the same kind of racks. And then the final kind of challenge we've run into is how do we deal with liquid cooling from a system integration and testing standpoint? So we typically want to have a rack that's rolling ready to the data center. So it gets tested in an external system integrator facility. And then we ship it to the data center, and they just want to roll it in, plug it in, and start things up. With liquid cooling, that becomes a little more complicated. And so we're still working through some of the challenges. Do we fill on site, or can we ship it filled? Is there any additional testing that needs to be done on site? That sort of thing.
Okay,
I think that's it for me.
Okay, so last but not least is Patrick from OVH Cloud. Please, Patrick. Yeah.
Yes, I'm Patrick Mayo. I'm a distinguished engineer at OVH in France, and I've been with OVH for 5 years now, working in the R&D, the industrial side of R&D, as opposed to the IT side of R&D. And a thing that we have done very differently at OVH from day one is basically all our servers are water cooled. When I say all, it's probably 95 or 96% of them are indeed water cooled. Our racks are very different from a lot of what you could see in the industry. They're horizontal and they're stacked. So we actually have 3 or 4 stories of racks, and they're all water cooled. So some of the challenges and issues that some folks actually have mentioned here are really true. It's very difficult to integrate things coming from different vendors, and they're not compatible, basically. They're not meant to be compatible originally. Hopefully, some efforts like what OCP is doing is going to bring, basically things to become compatible, and that's a good move. But as a result, and very early on, OVH decided to actually be a full integrator of its own systems, and that's how we managed to actually have the capabilities to make our servers, make the water cooling facilities, the water cooling systems, and have that standardized all across the data centers that we have at OVH. So it's been a major challenge over the years, and we've managed to have 20 years of water cooling with happy and less happy, but most of the time very happy systems, and that's a good experience.
Okay, thanks, Patrick. So if we could go to the next slide, I'm going to start with a couple of questions that we've been discussing beforehand at the panel, and as a result of our discussions. So the first question, and I'm going to target the questions to particular panelists in the interest of time, because we don't have that much time. So first of all, one of the things that came up is what kind of additional monitoring or data collection do you really need for liquid-cooled solutions? So I think, Patrick, you're probably well versed to start this off, if I could hand that question to you.
I can actually start talking about this. Monitoring is key. Let's say that if you have an air-cooled system, you have a temperature of your system to take care of, and you take care of that basically with the whatever air cooling you have and ventilation and so on. Water cooling brings basically still temperature to monitor anyways, except you have to monitor it at the chip level. If you do direct plate cooling, you have to monitor it also at the CDU system level, and you have to monitor it outside because you're dependent on the environment. Probably even more than with just air cooling, where you have air vacuum systems, not air vacuum, HVAC systems, and you have all those facilities that take care of making sure that you have some cold air around. But on top of that, there are some other elements that are involved in the water cooling, such as pumps and so on, and this actually brings tons and tons and tons of data that you have to monitor and make sure that you can react correctly on whatever, wrong value or failure that you have.
Okay, yeah, that's very important. Yeah, Tim, do you have any views on this as well? I think you mentioned some things about monitoring from your perspective as well.
Yeah, because we were using different technologies. One of the points mentioned earlier is the fact that a lot of these solutions aren't particularly made to work together. So we decided to think of, from a standards perspective, let's see if we can get some form of common language between all the different technologies. And whether it was the right products or not, we actually decided to make everything Modbus. So we worked very close to the manufacturers that we could actually get a Modbus interface into everything, because go back to what Patrick was saying, we need to be really careful of checking for changes in temperature, but we were cascading heat between these different technologies, and they all need measurement in different ways. So we wanted some sort of common solution. We did actually write a BMS solution as well, which allowed us to actually not only monitor the site, but allow us to start to try and test to see what changes were made. So part of our bit from a research perspective was to see what the effect was, because the effect when you merge in different liquids is a total different sort of effect anyway. But it then helped us with our operating practice as well, which we can talk about later as well, where liquid requires a bit more of a structured mindset as far as doing add moves and changes, and monitoring is key to making sure that what you do the rest of the data center does work in conjunction correctly.
Okay, Tim. Yeah, fair point. Yeah. So, Robert, I mean, as you mentioned, Microsoft is a bit newer to liquid cooling than others. What kind of things were you considering in terms of monitoring from your perspective?
I think Tim raised a good point about the intercommunication between systems. Usually we have data center systems that in our air-cooled data centers that are kind of monitored and operated on their own. And then we have server-side monitoring. And when you're bringing in facility water directly into the servers, now you're kind of having to merge those two systems. And so how we merge those monitoring systems or how we get them to communicate together is definitely a challenge. At least we already heard, I think Tim mentioned Steve mentioned the lack of leakage, but facility managers tend to be pretty conservative in general. And so when we come in, that's often one of the times, the first questions that we have is what happens with, if a leak happens, how do we manage it? How do we monitor it? And so there's definitely a lot of discussions going on about how we look at leaks, what kind of containment we have to have, that sort of thing as we talk about going into facilities. Hopefully over time, if we see that that's a very reliable thing, that becomes less of an issue, but certainly as introducing a new system, that everybody starts pulling their hair out about that pretty quickly. So.
Yes, fair point. You've raised the four-letter word I was going to mention in the second question we have, which is leak detection is really obviously important for. So, what are the key approaches that are best to adopt in terms of the different technologies for leak detection? And I know that you have all the panelists have different experiences with the different solutions. So, Steve, from leak detection, okay. Your coffee machine leaked, but what are you doing for leak detection? Yeah.
Yeah, inside. So there are a couple things. So we've always deployed systems that have used negative pressure. So all of the liquids that were used for cooling that came in contact with the chips were all drawn under negative pressure, and so leaks took the form of sucking air into the plumbing rather than spraying valuable electronic components with water. I think it's easier to detect leaks in this sort of arrangement. You can do this sort of at the, with small groups of racks or at the row level. It doesn't have to be at a facility level, but you can detect a leak, localize it because of vacuum pump activity. If you're pulling air in, your vacuum pump is going to be working harder, and that sort of comes back to what are you monitoring? So you want to monitor the vacuum pump activity. Also, we insisted that our racks have the leak detection rope, if you will, inside. So if any water was detected, then that was through a connection all the way back to the panel. So if everything else failed, right, if all other safeguards didn't work out, we had leak detection at every level within the racks, and that would act like a ground fault interrupt in your bathroom, and it would shut the power to those racks off at the panel. Because the last thing you want to do is be searching for the source of a leak in an energized rack. So those are two metrics or two approaches that we took to minimize risk. Make sure your power goes all the way back and that it's turned off at the panel. And we consider a best practice to circulate liquids under negative pressure.
Mute again. Sorry. Yes. Thanks for that, Steve. Yeah, that's a very good point. So, Jessica, do you have anything to add to this aspect
Sure.
of leak detection? Yeah.
Yeah, leak detection and mitigation and intervention. It's one of those we've all concluded, right? It's one of those concerns that show up early. That's what users and customers are concerned about. So, and understandably so, right? If you're using water-based liquids for cooling, of course, that's electrically conductive. So you don't want that to spill out on any of your IT equipment. But I should also say there's also other applications, right, that are using dielectric cooling liquids as well, both within cold plate solutions as well as for immersion, right? And just wanted to bring that up because the leak detection will look very different there. You can't rely on that you have an electrically conductive detection, but you need to use something else, right? So it really depends on what the best solution looks like. It really depends upon what the customer wants. So really the approach there, I believe, should be that you're looking at doing a risk analysis of determining what are the risks and how much are you willing to pay for it, basically. Do you want to bring in leak detection and intervention into the IT equipment, into each node? That's going to be more costly, of course, than if you're keeping it on a rack level, for example, if we're talking about cold plate applications. So doing a risk analysis of trade-offs of what the costs are versus what the coverage that you're getting from it should be done. And just because it is such a kind of heated topic, of course, the cold plate focus group within the advanced cooling solutions, there's currently a focus group that is working on a white paper really that is aimed at educating, of saying, okay, depending upon what type of liquid and what type of application that you're dealing with, here are a few different options for leak detection and interventions. So people at least can be educated about the different options that are there. And then showcase also a risk analysis of this is an example of how you can do it. To make sure that they're making an educated choice as they determine what fits them best going forward.
Okay, thanks, Jessica. I mean, Patrick, 19 years of liquid cooling. Any confessions that you want to make? I mean, how have you dealt with the leak detection?
Leak detection has been a key element, and yes, in the early days of OVH, probably there's been a lot more failures than we have today, and we have very, very few today, and partly also due to the fact that we had over time our technology evolved, and it's like there are lots of comparisons that we could make with other elements in life, but if you want to avoid leaks, you just have to avoid gaskets, and things are screwed or assembled together. And over time, we came to the conclusion that, it has to be a single copper line without any connection, basically from the inlet to the outlet of the rack or the system. So we tried very hard actually working on that, making sure that we use only copper, that we do use soldered element only, and there are no screws, no gaskets, no nothing, in the server itself. That limits a lot the number of leaks that you could actually find one day in a rack. So that's one thing, but you still have to monitor for leaks, at the rack level, anyways, and that has a cost. I agree with Jessica on this, and you have to mitigate, how much you're willing to pay, basically, for a risk that may or may never come. And technologies today, in terms of the quick connections that we can have, which are dropless, most of them, made by very good companies that are doing this for a living, as well as full soldered elements. These make some very, very consistent and leak free for lots of years before you get any issue.
Okay, Patrick, yeah, thanks for that. Yeah, some good advice there. Yeah, so if we move on to the third question that I have here, and that's obviously we don't want to use liquid cooling for liquid cooling's sake. So what approaches should we adopt to pushing for an IT-driven solution, which I think is important. So I think, Robert, you might want to say something about this coming from a very mixed environment at Microsoft there.
Yeah, I think the way we view liquid cooling at Microsoft is like you said, we need to adopt it where it needs to go. And what we're seeing in the next generations of processors and compute hardware coming down is that there's powers are increasing, case temperature requirements are going down, and it's the thermal requirements that are really driving us into going to liquid cooling. When we get to as far as a server design, we talked about a lot of the interaction between how elements that were kind of isolated on their own. A server in air cooling is often kind of viewed as its own point in a rack, and then a rack is kind of viewed on its own point in a data center. A lot of that a lot of those components those lines get a lot more blurred in liquid cooling systems. And I think, as Jessica mentioned, you have to look at it as more of a holistic view from the facility down all the way to the server level to get everything integrated and communicating together. And so there's a lot of systems that need to be revisited as far as management, monitoring, to get all those systems communicating together. And then a challenge that we're probably going to run into for a while is there's still demand for a lot of air-cooled systems as well. And so as we develop liquid-cooled systems, we're trying to develop something that can sometimes serve a dual purpose. If we have a air-cooled system, we would design an air-cooled system that could accept or be retrofitted or converted to liquid cooling, so we can kind of use a common designs around there, and then upgrade to processors or other things that have liquid cooled requirements. And so there's still a lot of mixed requirements coming from both the air cooling and liquid cooling side as we start to adopt and delve more into liquid cooling.
Okay, Robert. Yeah, and then Jessica, from the IT perspective, would you have something to say about IT-driven solutions, the use of liquid cooling here?
Yeah, I agree with Robert as well, right? It's the integration of the liquid cooling solutions that really needs the attention. We can't operate in silos when it comes to IT equipment and the rest of the loop, right? There needs to be someone that is in charge that really knows what the different materials, be able to establish what all of the wetted materials are, and if they are compatible with the cooling liquid that is being used. So you avoid any type of potential issues with that, right? And then, of course, it's really different requirements if you're dealing with cold plate solutions, or if you're dealing more of immersion solutions for liquid cooling as well. For more of cold plate solutions, again, it need to really do an analysis of what it is that you want there, because again, you might be able to take heat out of the CPU and the DIMMs in order to be able to reduce the fan speeds a lot, right? So the operational costs will go down going to liquid cooling, but you also need to look at the hardware costs that you and really need in order to procure the cold plate, the liquid cooling solution, as well as the DIMM liquid cooling solutions for that, right? So doing that type of analysis and how much of the heat that you would like to capture within the liquid versus the air. For immersion, you get into more of really if generating more of an optimized IT design. So we've had discussions on that topic earlier here today as well. You don't need any fans, right? But for installation of immersion, you need the tanks and you need the liquid instead. So really looking at what not only the cooling capability, but also what the costs are in order to get equipment, and both from a capital expense as well as an operational expense. So it's different requirements. If you deal with cold plates versus immersion, they will likely want to have different type of IT equipment, right? And potentially changed out, put some materials as well to ensure compatibility with most liquids. But that's really the integration as a full system. I just want to stress that again as the highest importance for liquid cooling.
Okay, thanks, Jessica. Yeah. So, I mean, often liquid cooling is associated with the fact that we have elevated temperatures and the opportunities of getting reusing the energy. So I think, Steve, you might have something to say about energy reuse and your experiences.
Yeah, thanks, Sean. As I mentioned in the opening, that was a part of our design from the beginning, was to capture and reuse the waste heat. And if you're you want to work with the thermodynamics, then you've got to keep it, not have air to liquid in any step of your cooling system. It's all got to be strictly with liquid. So we use it for heating office space. As I mentioned, we use the active chill beam for space heating. We also use waste heat captured. We've got glycol loops for snow melt around our research building. So the walkways and plaza around our facility are ice-free in the winter because of that. So liquids by far give you the best option as a working fluid. Liquids provide distance, and they allow you to capture waste heat at higher temperatures than if you were strictly air cooled. So yeah, but the only way to reuse it is to use liquid cooling as your primary way of keeping your servers cooled.
Exactly. Yeah. I think that's one of the great arguments for it. I think Tim might have something to say about this. Tim, are you there? Yes. Oh, yeah. You're obviously relaxed there.
Yeah, I was just listening actually, because I think I'd like to link this back to the IT usage as well, because one of the things we were determined to do was, has just been said there, was make the energy use, as in reuse all the waste heat, as part of the main data center design. If you think link that back to IT use, the reason we did a hybrid system is the fact that certain servers, certain applications don't actually work that well at this moment in time with immersion. But by making a hybrid solution, we could get the IT into the light cooling environment, but put the immersion at the end. So we could actually raise that temperature and reuse the heat. And I think it's an important stage of, once you start going into things like immersion, that you have got that option, that you can actually get a usable byproduct. And I think that's really an important aim, is to try and get something out of that data center rather than just waste it. And if you do cascade and mix and match technologies, it allows you to add that as a byproduct. And I think it's a really important piece, that the environmental side of that, the reuse of heat in the buildings, especially in colder climates as well, is really important.
That's a very good point, Tim. I think you had that on your slide, didn't you? That temperature chaining concept. If I could go to the next slide, I wanted to just, as a shout out at the end here for the call to action, but while that slide is up, I wanted to just check whether there were any questions from the audience. I'm not sure whether I get that through the chat or through the FNU. Are there any questions from our participants to the delegates, to the panelists here?
Yeah, Rolf here, Rolf Brink.
Trust you, Rolf, yeah.
Sorry.
No,
in response to the comments by Patrick on with the OVH background, when you did the introduction, Patrick, about the fact that you have a lot of experience with technologies being proprietary and not standardized. I would like to get your opinion on which the key aspects are that you see to standardize on across technologies. I'm not talking about making them all the exact same product, but which aspects of the technology would you be looking for as a primary goal to standardize on?
Interconnections are key, and I think one of the key aspects, and it's been discussed actually over the panels, is the connections between the whatever tubing you have between the CDU and the racks and so on. And if you want to have any type of capability of exchanging or upgrading a server by another one, you want to have that compatibility at that level. The world has been almost able to do it for electricity. Still not yet there, by the way. We don't have the same plugs, we don't have the same value for voltage and so on, but still we managed to basically have, or we're still able to exchange electricity across countries and so on. To some extent, we have to get to the same level of agreement between companies, between whoever manufactures those dropless connectors and whoever manufactures the pipes and so on, so that things get compatible at some point. To me, this is the key. The rest of the technology, we're going to buy computers from or CPUs from one company, or memory from another, and so on. The form factor will differ and will evolve with time, but at least at the big component level, such as a server, we must have compatibility.
So are you, Patrick, does yourself or any of your colleagues interface with the OCP on the ACS or the ACF?
We do, yes. We have a few people actually participating to some OCP.
So that would be
yeah,
a good way of passing on that information.
Yeah,
I think we've
Exactly
actually run out of time. I'm sorry, it's a very compressed time, but I'd just like to take this opportunity to thank all the panelists for their time in this interesting few points that we've covered today, and also to thank Amelia Coverdell from Asperitas and Archna Haylock for helping me set this up. So thanks, guys, and have a good rest of the day. Yeah. Patrick, it's almost midnight for you, isn't it?
It's past midnight.
It's past midnight for you, yeah.
Good rest of the night.
Thank you, guys. Yeah. Okay.
Thanks, everyone.
Thanks a lot,
Thank you.
everyone. Yeah.
Appreciate it.
Thanks a lot.